Question 6b. A fire hose is at ground level on a horizontal plane. Water is projected from the hose. The angle of projection, theta, is allowed to vary. The speed of the water as it leaves the hose, v meters per second, remains constant. You may assume that if the origin is taken to be the point of projection, the path of the water is given by the parametric equations x equals vt cos theta, y equals vt sin theta minus half gt squared, where g meters per second squared is the acceleration due to gravity. Do not prove this. Part 1. Show that the water returns to ground level at a distance v squared sine 2 theta over g meters from the point of projection. The height of the water at ground level is 0, which means y equals 0. Hence, x equals vt cos theta, we'll call this equation number 1, and 0 equals vt sin theta minus half gt squared. And we'll call this equation number 2. Now the idea is to solve equations 1 and 2 simultaneously by eliminating the parameter t. So from equation number 1, making t the subject, we get t is equal to x over v cos theta. And from equation number 2, we can divide all terms by t first. So we have 0 equals v sin theta minus half gt. Then making half gt the subject, we get half gt is equal to v sin theta. And then dividing both sides by half g, we get t is equal to 2v sin theta over g. Note that dividing by half is equivalent to multiplying by 2. And we'll call this equation number 3. Now equating equations 1 and 3 via t, we get x over v cos theta is equal to 2v sin theta over g. Now we're going to make x the subject. So multiplying both sides by v cos theta, we get x is equal to 2v squared sin theta cos theta over g. And note that 2 sin theta cos theta is equal to sin 2 theta. So that's the double angle identity for sine. So x is equal to v squared sin 2 theta over g. Therefore, the water returns to ground level at a distance v squared sin 2 theta over g meters from point of projection as required. This fire hose is now aimed at a 20-meter high thin wall from a point of projection at ground level 40 meters from the base of the wall. It is known that when the angle theta is 15 degrees, the water just reaches the base of the wall. Part 2. Show that v squared equals 80g. It is given that x equals 40 meters when the angle of projection theta equals 15 degrees. Substituting x equals 40 and theta equals 15 into the formula that we found in part 1, that is x equals v squared sin 2 theta over g, we get 40 equals v squared sin 2 times 15 degrees over g. Now 2 times 15 is 30, and multiplying both sides of the equation by g, the equation becomes 40g equals v squared times sin 30 degrees. Now sin 30 degrees of course is half, so we have 40g is equal to half times v squared. Multiplying both sides of the equation by 2, we get v squared equals 80g as required. Part 3. Show that the Cartesian equation of the path of the water is given by y equals x tan theta minus x squared sec squared theta over 160. From part 1, t is equal to x over v cos theta, and we're going to substitute x over v cos theta into the parametric equation for y, that is, y is equal to vt sin theta minus half gt squared. So replacing the parameter t with x over v cos theta, we get y is equal to v times x over v cos theta times sin theta minus half g times x over v cos theta squared. Now this v and this v will cancel. Sin theta over cos theta is tan theta, and bringing the squared inside the brackets here, we get y is equal to x tan theta minus half g times x squared over v squared cos squared theta. Now 1 over cos squared theta is sec squared theta. So the equation becomes y equals x tan theta minus half g times x squared sec squared theta over v squared. Now note that v squared is equal to 80g from part 2. So replacing the v squared with 80g, the equation becomes y equals x tan theta minus half g times x squared sec squared theta over 80g. Now this g and this g will cancel, and the 2 here will multiply by the 80 here to give you 160. So the equation becomes y equals x tan theta minus x squared sec squared theta over 160 as required. Part 4. Show that the water just clears the top of the wall if tan squared theta minus 4 tan theta plus 3 equals 0. The top of the wall corresponds to the coordinates 40, 20. That is, x equals 40 and y equals 20. Now y equals x tan theta minus x squared sec squared theta over 160, which is the Cartesian equation that was found in part 3. Substituting 20 for y and 40 for x into this Cartesian equation and expressing sec squared theta in terms of tan squared theta using an appropriate Pythagorean identity, the equation becomes 20 equals 40 tan theta minus 40 squared times 1 plus tan squared theta over 160. Now 40 squared over 160 is equal to 10. So expanding the brackets, the equation becomes 20 equals 40 tan theta minus 10 plus 10 tan squared theta. Subtracting 20 from both sides, we get 0 is equal to 40 tan theta minus 30 plus 10 tan squared theta. Dividing all terms by 10 and switching both sides of the equation around, we get tan squared theta plus 4 tan theta minus 3 equals 0. Therefore, the water clears the top of the wall if tan squared theta plus 4 tan theta minus 3 equals 0 as required. Part 5. Find all values of theta for which the water hits the front of the wall. From part 4, the water clears the top of the wall when tan squared theta minus 4 tan theta plus 3 equals 0. Solving for tan theta by treating this as a reducible quadratic equation and factorizing the left-hand side, we get tan theta minus 3 in brackets times tan theta minus 1 in brackets equals 0. Solving tan theta minus 3 equals 0, we get tan theta is equal to 3. And taking the inverse tan of both sides, we get theta is equal to 71.565 degrees, correct to 3 decimal places. Solving tan theta minus 1 equals 0, we get tan theta is equal to 1. Taking the inverse tan of both sides, we get theta is equal to 45 degrees. Now we know that the water hits the bottom of the wall when theta is equal to 15 degrees, as this is given in the question. Combining this fact with this result, theta is equal to 45 degrees, the water will hit the wall for values of theta greater than 15 degrees and less than 45 degrees. Now there is another value of theta where the water will hit the bottom of the wall. It's not just 15 degrees. Now from part 1, we have x is equal to v squared sine 2 theta over g. And the bottom of the wall is 40 meters away from the point of projection. So we know that x is equal to 40 when theta is equal to 15 degrees. That is, 40 is equal to v squared sine 30 degrees over g, where 2 theta is equal to 30 degrees. But sine 30 degrees is equal to sine 150 degrees. This is a quadrant 1 angle, that's a quadrant 2 angle. So sine 2 theta is equal to 150, hence theta is equal to 75 degrees. Beyond theta is equal to 75 degrees, the water does not reach the wall. So combining both results, we have the water hits the wall for theta greater than 15 degrees and less than 45 degrees, or values of theta greater than 71.565 degrees and less than 75 degrees.